Welcome to Topology, Lesson 1. In this lesson, I'll provide several definitions of topology, and then I'll talk about an example which isn't in the mainstream of topology, but I think illustrates some of the main ideas. We'll spend most of our time on that example. And then at the end of this video, I'll describe very briefly what to expect from the following videos in this series. Topology is the study of shapes and spaces under the condition that you can stretch, squeeze, and compress the shape and it'll still be topologically equivalent to what you started with, but you're not allowed to break it or cut it. So what we have here on the right is an example of that. We have a coffee mug, and we can compress it where the cup part is becoming smaller and smaller. We're not doing any tears or breaks, and then eventually we get to a donut or a torus. The technical term is a torus. So these two, these two objects are equivalent from a topological perspective. Of course, from other points of view, they're not, but from a topological perspective, they're equivalent. So we're going to talk more about this in this lecture and in the following. And for a good introduction, in addition to what I'm providing here, there's a YouTube video, Intro to Topology, Turning a Mug into a Donut. And I'll provide the link in the description of this video. So I took some definitions from dictionaries and Wikipedia just to give you a flavor of what topology is. These are pretty much equivalent definitions, but they use slightly different wording. So let's look at the one from Wikipedia first. Topology, from the Greek word, and I'm not going to try to pronounce that, but it means place and then study. So study of place or location is concerned with the properties of geometric objects that are preserved under continuous deformation, such as stretching, twisting, crumpling, and bending. That is, without closing holes, opening holes, tearing, gluing, or passing through itself. So you can basically think of it as sort of a putty or a Play-Doh that you can bend and twist, but you're not allowed to tear it or break it. And you can compress it so you can make it smaller, which is something you can't do with Play-Doh, but just to kind of give you a mental image. Then we have another definition from the online dictionary, Farlex. Topology is a study of certain properties do not change as geometric figures or spaces undergo continuous deformation. These properties include openness, nearness, connectedness, and continuity. So these properties are something that we talk about in topological spaces. That'll come later in the video series. We're first going to just talk about surfaces, but this definition captures some of the more advanced aspects of topology. And then from Wolfram Math World, we have another definition. Topology is the mathematical study of properties that are preserved through deformations, twistings, and stretching of objects, and I would add compression. Tearing, however, is not allowed. We'll see in an example, you can tear an object and then put it back where the points meet each other in exactly the same way. But that's kind of a special case that we'll talk about. So in general, you're not allowed to tear, but like I say, there's some special circumstances which I'll describe in a future video. So they give an example here. A circle is topologically equivalent to an ellipse. You're just bending it into stretching it into a different shape. And a sphere is equivalent to an ellipsoid. So ellipsoid is sort of more of a rugby ball type of shape. A topological invariant is something immutable about a shape, no matter how we stretch or deform it. More formally, a topological invariant is a property of a topological space, a mathematical object that captures the basic idea of shape, that is preserved under a homeomorphism, which is basically continuous mapping. So to give you a more practical idea, let me just use an example here. So let's say we have this sphere at the top, and a homeomorphism would be just multiplying all the points by, say, a scaling factor of 0.8, and you might get this thing here. So the transformation would be just compression, basically, and you would go from here to here, and then you can do another scaling and get this smaller sphere and then this smaller sphere. So these are all topologically equivalent, and there's a fairly simple mapping that would get you from one sphere to the other, and vice versa. That's the comment here about invertible. So some of the examples of invariance we have listed here. Connectedness is pretty obvious. That's just the number of pieces you have. So if you have one object that's 3 pieces and you bundle them together and connect them and just get one piece, then the two objects are topologically different because you have to have the same number of pieces to be topologically equivalent. Compactness is a little bit harder to describe. It's basically an abstraction of closed and bounded from Euclidean space. I have a little example here where you have, say, a disk and its boundary. So this would be closed and also bounded. And then if you remove just the boundary, then it would be bounded, but it's no longer closed because you don't have the boundary included in your object. So this one is compact, this one is not, and by the definition of compactness, these two are not the same. Another example would be a straight line that goes indefinitely in either direction, in either Euclidean 2 space, Euclidean 3 space, and that would be unbounded, so it would not be compact. And then genus is something we kind of hinted at with the coffee mug and donut. It's the number of holes, so that's another invariant. If you have an object with 1 hole and another object with 2 holes, then they're have a different genus and they're not topologically equivalent. And we'll see some examples of that later on. So the next few slides, we're going to do an example of something that, as I mentioned before, is not really in the mainstream of topology, but I've seen it in a few books and a few papers, and I think it illustrates some basic ideas in topology. And so we'll go through that. The basic idea is simple. What we want to do is topologically classify the letters of the alphabet, and it does depend on the font you use. Different fonts may lead to different classifications. So just as an example from what we've said so far, the letter D and the letter O you would expect to be topologically equivalent because you can just bend one into the other. And for example, you can take an I and bend that into a J, and so you would expect those to be topologically equivalent. So we're going to make some statements, some assumptions first, and then we'll classify the whole set of the letters of this type here. Just keep in mind, we're assuming these letters are one-dimensional, so there's no thickness to the letters, and they exist flat within two-dimensional space. So they're basically one-dimensional objects embedded in two-dimensional space. And I give another example here at the bottom. The letter C, even though it doesn't look very much like a Z, you can twist that and bend it and think of something like a pipe cleaner that's flexible and you can bend it and it'll hold its shape. So these would be homeomorphic. We need to define the invariance for our problem at hand, and that's what I'm doing on this slide here. So Letters are homeomorphic, basically topologically equivalent, if they have the same number of holes. So as we mentioned on previously, D and O, for example, would have the same number of holes. So they would, at least in terms of the number of holes, they would be equivalent. And in fact, when you see the rest of what we're defining as invariants, D and O are actually invariant under these other properties also. The other topological invariant is the number and type of vertices in a letter. In this context, a vertex is a point where multiple lines intersect. The number of intersecting lines at a point determines the vertex type of a point. So, for example, the letter T has a vertex where the 3 lines intersect. So right here, you have a small line here, and then the longer line going down. So we would call that a 3 vertex. The letter K and also the letter X, you notice they have 4 lines coming in at one point. So that would be a 4 vertex. So the letter with the 3 vertex, like T, would not be equivalent to or transformable into a letter like K, which has a 4 vertex. It is not allowed in this particular topology that we're defining to change the vertex type of a point, so we can't morph a T into an L. So we can't like shrink this little bit here and then, rotate it and flip it to get an L. That's not allowed. Each letter has an infinite number of 2 vertices, so you can just pick any point in T or K, and there's always two lines going in that way, and that's not very interesting. So we're not going to talk about the 2 vertices. And some letters have a 1 vertex. So for example, the letter I, if you go to the very point at the top and the very last point on the bottom, then that would be a 1 vertex. And again, that's not of particular interest. So it's really the 3, 4 vertices that are of interest in our analysis here. Another method to determine the type of vertex is to enclose the vertex in question with a circle or a neighborhood that includes the vertex in question but no other vertices of type 3 and above. Next, we remove the vertex and then count the number of separate lines, and that gives us the type of vertice. So we have 2 examples here. We have the letter R using our particular script, and we can encircle one of the vertices here of type 3 or greater. So we encircle that, then we remove the vertex, that one little point, and then we see that we have 3 lines going into that. And we could have done the same thing here with this vertex. We can do the letter Q as another example. So we encircle the one vertex of that's complicated, this one here. We remove the vertex, and then we see again that there's 3 lines going into it. So just one maybe caution or point just to emphasize that our analysis depends on the type of script that we use, the type of font we use. So if we, let's just go here. If we had this Q and which is another valid way of drawing a Q, if we had that Q, then of course we'd have another line here, and then when we did the analysis, we would have a 4th line. So in that case, it would be a vertex of order 4, a 4 vertex. So again, the type of script that's used was important. The other thing would be like some scripts have serifs like that. That really complicates the analysis. Now you got to count all these little serifs, and you could even be fancy and go back this way or come up this way, and then all of a sudden you have a bunch of 3 vertices that you need to work with. So we're intentionally using a font that doesn't have these complications. Let's do the analysis here, given our preliminary assumptions concerning the invariance. So the first set of letters, which are most of the letters, they have 0 holes, and all the points are 2 vertices except for the 1 vertices. So for example, the C has a 1 vertice at the top here and at the bottom, but the rest of the points are 2 vertices. And these could all, you can take any one of these and bend it into, or deform it into any of the other ones. What might be a little bit tricky is the M. You see there's like a bend here, a sharp bend. But if we use our technique from the last slide and we remove this point or this point here, you're just getting a 2 vertices. So it's not of any different from just, for example, removing, say, a point here from the L. That's also a 2 vertice. So there's an infinite number of those in all of these. And as I say, you can bend any one of them into the other. Then in the second set, the D and the O, which we've talked about before, they have 1 hole and everything else are 2 vertices. Then the E, F, T, and Y, we have 0 holes, and there's a single 3 vertex. So it would be the middle right there and the E. Same thing in the F, the cross here at the top of the T, and then the junction at the Y. So those 4 are classified the same. They're topologically the same in our topology that we've defined. Then P and Q have 1 hole, and they have 1 3 vertex here and here. We mentioned K and X before. They have a 4 vertex. Everything else is either a 1 or a 2 vertex. H is kind of unique. It's in its own category. It has 0 holes and then 2 3 vertices, 1 here and 1 here. The A and the R have 1 hole each, and A has a 3 vertex here and here, and R has 1 here and then here. We saw that in the previous slide when we kind of blew up the size of the R and did the analysis. There would be another way of drawing an R like this, where you would maybe just come in here and then shoot right out. And in that case, you would just have this would be a 4 vertex instead of a 3 vertex. But the way we drew this one here, if you recall from the last slide, we drew it this way, and then we kind of branched off from here, so that these two are not topologically equivalent. Then the last one is B, and that has 2 holes, and it has 2 3 vertices. And again, that's the way we've drawn the B here. We could have drawn the B a little bit differently. I can show that here. If we drew it like where you kind of came in and then went out sharply like that, then this would be a 4 vertex, but we drew it sort of like the R, where we came in here and then came out there again. So that's just a 3 vertex. So these two, again, these two are not topologically equivalent, and we've chosen this one for in the font type that we selected. Okay, so there we have it. It's, again, this is not in the mainstream of topology. You won't see this everywhere, but occasionally some books will do this as kind of a starting point to give you an idea what we mean about bending and holes and what might be equivalent, what might not be equivalent, depending on how we define different invariants. We can apply our invariants that we define for letters to different shapes. So I've done that here, just using some circles and lines. So this would have 3 holes, and then these 2 points here would be 4 vertices. This one has 4 holes, 1, 2, 3, and then this different shape in the middle is also a hole. And then we have 1, 2, 3, 4 vertices. And then this one here has 1, 2, 3 holes, and then 3 vertices here, 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 and here. So 4, 3 vertices. And if you want to try it on your own, I've given you 3 examples that you might want to analyze and categorize based on our invariants. And be careful of these interior shapes like this here. That's also a hole. As I mentioned, our analysis of the alphabet and the generalized configurations on the last slide assume the figures are one-dimensional configurations embedded in two-dimensional space, basically in a plane. If we allow for one-dimensional closed curves to be embedded in 3 dimensions, so where you can cross over without having intersections, that's called a knot. We're not going to cover that here, but I did cover knots in a previous book that I wrote. It's section 8 in Mathematical Vignettes, volume 2, and I've made all my books available, at least the electronic versions, available free. And here's the link. I'll also put it in the, or I've already put it in the introductory, the description of the introductory video that comes before this video. I have a clickable link there in the description, so you can get to my books. And the particular, I'll just repeat myself from what I said earlier, but the material for this series of videos comes from Mathematical Vignettes, volume 3, and that's the electronic version is also available at this location here. In terms of an overview of this video series, we started with surfaces, and that's pretty much what we were talking about in this video, and we'll do a few more videos on those. Then we'll follow that up with a series of videos on something called a metric space, which is a sort of a prelude to a topological space. It's sort of a simpler concept, and I thought I would do that first. And it basically has a metric space has a concept of distance, and we can talk about topologies under that constraint. But topological spaces don't even have a concept of distance, so they're more abstract, and we'll do that last, and there'll be a series of videos on that particular topic. So it gets more abstract as we move along, and after we finish with the surfaces, this will be much more theorem and axiom based. So it'll be a bit more technical and a bit harder to follow, but I'll try my best to simplify things.